Hello, I'm Neeraj. Today I will explain the concept of low rank adaptations. Actually, low rank adaptations are used in fine tuning the pre-trained large language models. Actually, when we train the large language models, we use huge amount of publicly available data, and as a result, it contains a huge amount of parameters, like millions and billions of parameters in the form of some weight matrix. So when we try to use those models for domain adaptation for a particular type of personalized tasks like personalized clustering, classification, for personalized question answering, sentiment analysis, causal reasoning, causal inferencing, for any kind of tasks, or for want to use those models on personalized data, then we need a fine tuning process. So fine tuning process is again like use the pre-trained model and use their transformer architecture used in those training to retrain some of the layers by using our data. So it contains forward pass and backward pass both. That's why when we use the complete data and try to update the entire weight matrix of the pre-trained model, it takes a lot of time and it consumes a lot of resources. That's why people prefer to use some quantizations or some clever mechanism to do this in such way that we can little compromise with quality. So low rank adaptation is a similar kind of technique. So here it is a definitions like low rank adaptations method that adapts the weight of a pre-trained large language models without updating all the parameters. Instead of modifying the entire model, it introduces the additional low rank matrices to capture the necessary changes that makes the fine tuning process faster and requires less computational resources. So this is the summary. Now we will try to understand that how low rank adaptations achieve this task. So this will be easy from this hands-on example. Suppose we have a original model that is coming from pre-trained models and having weight W. So second step is we have to get the low rank decompositions. Here low rank decomposition is not like a matrix factorizations or any kind of matrix decomposition techniques. We just select the low rank matrices, and the rank of matrices we select, it is just like a trade-off kind of thing. Means we generally select the rank in such a way that we can get the best quality in the performance. So we generally, for example, identify two matrices A and B. Then we calculate the change in the weight by multiplying them. And after that we update the weight of the original matrix by adding those changes. So here it will be easy to understand. Suppose this is a weight matrix. Just for simplicity, I took the 3 by 3 matrix. So this is the original weight matrix of a pre-trained model. Now we took two smaller matrices because this is a rank of rank 2. We have identified that based on our trade-off, we have identified that by selection of this kind of matrices, our model can show the best fine-tuning performance. So based on that, we selected A and B both. Now we will multiply A and B. So here A is 2 by 2 and 2 by 3 matrices. So multiplications will be 2 by 3 matrices. After that, we will try to add this delta W with the original matrix. So this is the addition, but as this is a 3 by 3 matrices and this is 2 by 3 matrices, so we cannot work on all three rows of this original matrices. So we will just consider 2 by 3 here and 2 by 3 here, and just we will add both. For example, this with this. So this is the additions. But for this we are considering that it will be as it is at the time of addition, but as this is a part of forward and backward pass, because all matrices will go with forward and backward pass, so there may be some minor changes possible in the another rows. So we are assuming that changes. So now we will try to understand that what are the benefit we are getting here. So here we have a 3 by 3 matrices. Suppose we take a similar 3 by 3 matrices and then try to update it. Then we will require a lot of computational resources. But here, even in just 3 by 3 and these smaller matrices, we are not directly computing anything for the last row. So we are just updating these matrices, intentionally updating these matrices. Others may be some bias or through some things, we can see some changes in the value with respect to the additions at the upper layer. So we are just changing in these layers. So our computational resources will be easy for this part only. Now suppose you have a billions and billions of parameters, and even just consider that you have a just 10,000 rows and 10,000 columns in a matrix, and if you are using the rank equal to 8, then you can imagine with such kind of calculations that how less amount of calculations you will do with respect to two scenarios. First is taking 10,000 rows and columns matrices and update all the weights, taking 10,000 rows and columns matrices and another smaller matrices, two smaller matrices A and B with rank 8, and then update the weight of this. Then you will easily imagine that if you have a billions of parameters and millions or billions of rows and columns, then taking the low rank matrices will highly reduce the calculation overhead. Now we will try to understand that how these matrix operations will be a part of the overall calculations. So these are the actual complete step of fine-tuning process. So we take the pre-trained process, we initialize the low rank matrices A and B. So we have a rank of matrices R. We take the forward pass the input data through the model and compute the output. We use the current values of A and B for adaptations. We can compute the loss, and after that in the backward pass we compute the gradient of loss with respect to A and B both. Means in the calculation of loss we will take the derivatives with respect to A and B both. And after that we will update the low rank matrices. Means we will update the A and B by using the optimizations algorithm like stochastic gradient descent and Adam optimizations. And after that we will update the matrices. So this calculation I already discussed earlier. And after that we update the original matrices. And we will repeat the step forward pass, loss computations, backward pass, and then update the low rank matrices, and then update the matrices weight for the low rank matrices by using the low rank matrices and add those with the original matrices and continue the cycle. And after some cycle we will have, for example, just like a traditional deep learning algorithms like you fine tune or train. So after 3 epochs, 4 epochs or some 10, 20 epochs, you can stop the process, or if you manage, you can control it through some loss functions also. So this is the process, and in the entire process, due to this kind of scenarios, these 3 steps that discussed here, the entire process will be less costlier than the process when we take the entire weight matrices. So now in the next tutorial, I will explain the same thing through some working example.